For today's lesson, we will be discussing about the sampling distribution of sample proportions. So before we proceed with the discussion about the sampling distribution of sample proportions, let's discuss first some of the concepts related to it. Let's start with the binomial random variable. So it is a type of a discrete random variable that counts how often a particular event occurs in a fixed number of trials. So when we say binomial random variable, this is a kind of variable wherein there's only two results whenever we do an experiment. So for example, tossing a coin. So it can only be heads or tails. Counting the number of true in a true or false test. So that is also an example of binomial random variable because the results may be true or false only. That's why it's called binomial random variable. And then it also counts how often a particular event occurs in a fixed number of trials. So for example, in tossing a coin, for tossing it for like 10 times, how many times will you get a head as a result, and so on. Now here are just some of the conditions for us to say that a particular variable is a random, binomial random variable. So first, there are a fixed number of trials or a fixed sample size. So for example, tossing of coin for 10 times, counting the items with true in a 10-item quiz. So there. So again, there's a fixed number of trials or a fixed sample size. On each trial, the event of interest either occurs or does not. We also refer to it as success or failure. So for example, in tossing of coin, so let's say the interest there, or the event of interest, or the one that you want to identify is the number of times that you will get a head by tossing a coin. So when you get a head, that is considered as a success, and if you get a tail, that is considered as a failure of the experiment. So on each trial, either the event of interest occur or it does not. So it's either you get a head or you get a tail. The probability of occurrence or not is the same on each trial. So the probability of you getting a head when you toss a coin is 50% or 0.5. And then on another trial, that is again 0.5. So it is the same for each trial. And lastly, trials are independent of one another. So if you toss a coin and then you get a head on the first one, if you toss again it for the second time and then you get a head, so you getting a head on the second toss is not dependent with the first result. So the trials are independent of one another. Now, this binomial random variables may be used in some experiments or researches. So it's really important that you know how to recognize whether the variable involved in a particular problem or situation is binomial random variable. Now, here are just some of the things that we have to consider, or the variables that we have to look for that is related with the binomial distribution. First, we have n, which is the number of trials, or this is also referred as the sample size. Then we have this two right here. We have p, which is the population proportion of successes. And then we have the q, which is the population proportion of failures. So a while ago, we discussed about the success and failure when it comes to the trials in binomial random variable. So these two right here, these are the variables that we're using to represent the proportion of success and the proportion of failure, or the probability of success, probability of failure. So again, for example, you have to toss a coin 10 times and you want to identify the number of heads that you will get, or the proportion of you getting a head when you toss coin 10 times. So let's say out of 10, so 4 out of 10, we're able to get a head. So that means that is the success, because that is our event of interest. We want to identify or count the number of heads that we will get. So this will give us now the value of p. So 4 out of 10, or 4 over 10, that is 0.4 or 40%. So that now is the proportion of successes. And then the remaining 6 out of 10 that means you're able to get a tail. And that is now the failure. So to get that, you will just subtract P from 1. So 1 minus 0.4, that will give us 0.6. Because again, in total, the probabilities should be equal to 1. So these are our P and Q. Again, they represent the proportion of success and the proportion of failure. Now, as you noticed, we have here P hat, this one right here. This P hat is for the sample proportion of successes. Like what I've said a while ago, we can use this binomial random variables in experiments, research, and of course it involves population and sample. So remember, P and Q, this is from the population, and then the P hat, this is the proportion of success from the sample. Now, to visualize everything, I will show you this illustration. So for example, we conducted a research or a survey. We conducted a survey. So this is our population. And from our survey, we're able to get or see that 60% of all our respondents prefer brand X compared to brand Y. Okay? So 60% of the population prefer brand X than brand Y. So that is now the proportion of success, or that will give us 0.6. So again, you have a population, and within that population, we can identify the proportion of successes of P. So example, 60% of this population prefer brand X or agrees that brand X is better than brand Y. Now, within this population, we can draw random samples of same size. So for example, the size is N. So if you get a sample from that population, now this sample right here, you can again compute for the proportion that is present in the sample, proportion of success. That's why we have here P hat. So this one symbolizes that the proportion that we have is from the sample. So out of the samples that we get, what now is the proportion of them agreeing that brand X is better than brand Y? So you keep on getting samples or drawing samples from the population with same size. So each sample, they have the corresponding sample proportions. So another one, and then another sample proportion. So there can be a lot of samples that we can draw from a population. And remember, each sample, they have their own proportion of successes. So if we will list down all of these proportion from our samples, then we will come up with the sampling distribution of sampling proportions. So it is the distribution of values of the sample proportions P hat in repeated samples of the same size. So again, from the population has its own proportion of success. And then we draw samples with the same size, and each samples, they can have their own proportions. So which is represented by P hat. And then if you list down everything and then you count all of the sample proportions that you can get from all of the samples of the same size, then we will end up having sampling distribution of sampling proportions. Now take note that the mean of the sampling distribution of sample proportions is equal to the population proportion of success. So this one. So like what I explained a while ago, each sample has its corresponding proportions, and we can get the mean of all of those proportions from our sampling distribution. And the mean of all those sample proportions is the same as the population proportion of success. So they are just the same, or they should be equal with one another. So that is one thing that we have to remember with sampling distribution of sample proportions. Another one is that the standard deviation of the sampling distribution of sample proportions is given by this formula. So here we have square root of P and Q, or P times Q. So P is the population proportion of success, Q is the population proportion of failure, all over N, which is the sample size. So this is the formula that we will use for the standard deviation. Now, the sampling distribution of sampling proportions is approximately normal if N times P is greater than or equal to 10 and N times Q is greater than or equal to 10. So we can say that our sampling distribution is normally distributed, or we can assume that it is approximately normal, as long as if we multiply the sample size with the population proportion of success and also the sample size with the population proportion of failure, they are both greater than or equal to 10. So if we already identified these two and then they are both satisfied, then we can already assume that our sampling distribution of sample proportions is normally or approximately normal. So since we already assume that it is approximately normal, so we can now use again the concepts that we know. We can apply it now. So based on the concepts that we know about the normal curve, so we can already apply it with these problems. So first is of course the z-score. So for us to convert a data into its corresponding z-score, knowing that the data that we have are sample proportions, so this is the formula that we have to follow. So we have p hat, which is the sample proportion of success, minus, and then this one is the mean of the sampling distribution of sample proportions, and then all over the standard deviation of the sampling distribution. So this is the formula on how we can get or convert a particular data or sample proportion into its corresponding z-score. We can also rewrite this formula as z equals, so we still have the p hat minus, now instead of writing this mean of our sampling distribution of sample proportions, we can change it to p, which is the population proportion of success, because a while ago we mentioned that the mean of the sampling distribution of sample proportions is just equal with the population proportion of success. So we can write it like that, all over, and then we have the standard deviation, so we can just write the formula for the standard deviation, which is P times Q all over N. So this is an alternative formula that we can use, so that we can just go directly and substitute all of the values that we have. Let's try this example. In a particular survey, 80% responded yes. What is the probability that when a sample of 500 people is observed, the proportion of people saying yes is less than 78%? So in this case, so we have the population, and from the population, after conducting a particular survey, 80% of them responded yes. Now, if we will get samples of 500 from that population, so let's say you get a sample of 500 from that population, so each sample, they will have their own population proportion. So another set of 500, so that's another population or another sample proportion of success, and then another set of 500 samples, again that's another set of sample proportion of success. Now, if we will identify all of these sample proportions, what now is the probability that the proportion of people saying yes is less than 78%? So that is what we want to identify. So from the sample of 500 people observed, so we have to identify what is the proportion or the probability that the proportion of people saying yes is less than 78%. So what we will do is we have to identify first what is our success and failure of the experiment. So here, since we know that in a survey 80% responded yes, so maybe the other one is no. So yes is our success of the experiment, and then no is the failure. So with that, we know that P is for the success and then Q is for the failure. So success, that is for those who said yes or responded yes, and then Q is for the failure, so those who responded no from the survey. So P and Q, this will came from our population. So the value of P now, since 80% responded yes, so we represent it using decimals. So this one is 0.8. So that now is the population proportion of success. Since again, 80% of the population responded yes from a particular survey. Now how about Q? So Q is just 1 minus the P, or since this one is 0.8, so the remaining 0.20 will automatically be our Q. So that is now our Q. Then, next thing that we have to do is, let's write down N, or the sample. So we have 500. And then, we want to identify the probability that the proportion of people saying yes is less than 78%. So, P hat is less than 0.78. There. So, this is what we want to identify. Now, before we start solving, we have to make sure first that this is normally distributed. So, we have to check. So, multiply N with P. This should be greater than or equal to 10. And Q, and it should also be greater than or equal to 10. So let's write here, N is 500 times P, which is 0.8. So this should be greater than or equal to 10. N is 500, and then Q is 0.2. So this should be greater than or equal to 10. So for this one, 500 times 0.8. So this one is 400, and that is greater than or equal to 10. So correct. This one is 100, and that is greater than or equal to 10. So correct also. So since the conditions were satisfied, we can now assume that this is normally distributed. So we can now apply the things that we know about the normal distribution. And that is using the z-scores. So let's now convert. So we will be using the formula P hat minus the population proportion of success all over the formula for the standard deviation, P, a square root of P times Q all over N. So let's substitute the values that we know. So our P hat, so since what we want is to identify the probability that the proportion of people saying yes is less than 70%, so our P hat will be 0.78. So 0.78 minus our population proportion of success is 0.8 all over, and then square root of P, 0.8 times 0.2 all over N, which is 500. And then just solve this and then round off to 2 decimal places. So you should get negative 1.12 as our z-score. Now, after that, so let's draw our normal curve. So here in our normal curve, the values that this one shows are the sample proportions. Okay, the probability of our sample proportion. So just take note of that. Again, this normal curve shows us the probabilities of our sample proportions. So let's say this is 0, and then we have negative 1.12. So this one. So this is the shaded region because less than 78%. So that means we are getting the left side of our z-score. So you just have to look at your z-table and look for the area of negative 1.12 that will give us the probability. So that is 0.1314, and if we just convert this into percentage, that is 13.14%. So that is now the probability that the proportion that we will get from our sampling distribution will be 78 or less. Another example, a survey result shows that 80% of respondents agree on a certain school policy. If 50 samples are taken, what is the probability of observing a sample proportion equal to or greater than 90%? So here, our event of success is the respondents that agree on the certain school policy, and then the failure will be those who disagree. So here we have P. So our population proportion of success is we have 80%, so that means it's 0.8 here. And then for our failure, proportion of failure, so that is 0.2. So that in total we have 1. And then our N is 50. So that's the sample size. And later we want to check what's the probability of us observing a sample proportion equal or greater than. So greater than or equal to 90% or 0.9. So this is what we want to identify. So let's check first if this is normally distributed. So let's multiply N and P. And then we will also multiply N and Q. And see if it's greater than or equal to 10. So for the first one, this is 40. So it's greater than or equal to 10. And then we have 10, also greater than or equal to 10. So that means the data that we have is approximately normal. So let's now solve for the z-score. So p hat, since what we want is 90% or above, so our p hat is 0.9 minus the population proportion of success, which is 0.8, over, and then we have the square root of P times Q all over the sample size, which is 50. So again, solve for this one and round off to 2 decimal places. So we will get approximately 1.77 as our z-score. Now, let's draw the curve. So we have here the 0 and then 1.77 here. Since what we want is 90 and above, so that means we will be considering the area to the right of our z-score. And to solve for this, you have to get the area to the left of 1.77 and subtract it from 1. So 1 minus the area of 1.77. Because again, as what we know, in our z table, what we have there is just the area to the left. So for this one, 1 minus, and then the area to the left of 1.77 is 0.9616. So just refer to your z table, then subtract, you will get 0.0384. And if we convert this into percentage, so that's 3.84%. So this is now the probability of us getting a sample proportion that is 90% or above, given that the sample size that we have is 50. And for our last example, in a particular survey, 60% agreed in a particular statement. What is the probability that when a sample of 100 people is surveyed, the proportion of people agreeing the statement is between 56% to 64%? So again, the event of interest here is those who agreed in the particular statement, and the failure here is those who disagree. So the value of P is 0.6, since we have 60% of our respondents who agreed to the statement. And then for the Q, so since this is 0.6, so the remaining will be 0.4. And then our sample size will be 100, so here. And what we want to know is the probability that the proportion of people agreeing the statement is between, so the proportion of our sample is between 56 or 0.56 to 64% or 0.64. So there. So let's check again if it's normally distributed. So 100 times 0.6. If it's greater than or equal to 10. So this one is 60. It's greater than or equal to 10, correct? And then 100 times 0.4. Then greater than or equal to 10. So this one is 40, which is still greater than or equal to 10. So this is assumed to be normal or normally distributed. Now let's solve for the z-scores. As you notice, we have there two boundaries, the 0.56 and also the 0.64. So that means we have to convert two z-scores. So first, 0.56 minus the population proportion of success, which is 0.6, all over, then formula for our standard deviation, 0.6 times 0.4 all over our sample size, which is 100. And then the other one, we have to solve for 0.64 minus 0.6 all over square root of 0.6 times 0.4 all over 100. So the values that we will get here is, so we have for the first one negative 0.82, and for the other one we have 0.82. So since we now have two z-scores, so if you draw in our normal curve, so you have 0, so this is negative 0.82, and then this one is 0.82. And then we need to get the area between the two, and that area will give us the probability. So all you have to do is to get the area of the larger z-score, which is 0.82, area to the left, and then subtract to it the area to the left of the other z-score, which is negative 0.82. So for the first one, so the area of that is 0.7939 minus 0.2061. So again, just refer to your z-table and look for the areas of this z-scores to the left. And then we will have 0.5878, and that is 58.78%. So that is now the probability that we will get a sample proportion that is between 56% to 64%, given that the sample size is 100. So that's it for today. I hope you learned something about the binomial random variable as well as with the sampling distribution of sample proportions, and see you next time.